So my document, if you actually look at it, it says there's 9 pages. We're not going through all 9 pages. I only printed off what we'll go through. Okay. What I'm taking a look at is I'm trying to find applications in real life that fit quadratic situations. And here it says, in the United States, the most common measure of lumber volume is the board foot. If you've ever worked in construction, you probably know so. A board foot is defined as a piece of wood containing 144 cubic inches. It can most easily be visualized as a board that is 12 inches square and it's 1 inch thick. Numerous methods called rules have been developed to estimate board foot tree volume. These rules provide an estimate of the board foot content of a tree based on tree trunk diameter at breast height. So what they do is when someone goes up to a tree and at the height that's your chest, they measure the diameter, which is the distance across the tree, and they can determine if that tree should be cut down or not. It should be harvested, which is good because we don't always want clear cutting. We instead want to make sure that they're cutting according to what's good for the economy and good for the environment. So the table directions say the table of data provides the number of board feet that can be anticipated from a tree in respective diameters. Plot the data from the table on the chart. So on the left-hand side, the column is labeled diameter of trunk breast high in inches. And we can see in the first row that the diameter of a tree is 12 inches. Across from that is the number 50. And that column is labeled number of board feet. So if a tree is 1 foot across, they can anticipate about 50 board feet coming out of it. What I would like you to do is to take time and plot the different ordered pairs that you see on the table to the right. I already put 2 values in there because I had to have 2 values for Excel to give me this graph. Okay, so I'll just go ahead and give you some time to try to plot. Oh, I'm going to pause here. I just noticed something that it did on me. All right, we noticed that the table had some weird values on it, so I've adjusted it. The bottom numbers were counting by 5s, and this is the trunk in diameter. And then the vertical axis, we had to count by 200s, and that's the number of board feet. What was that? Oh, thank you. And so take time to plot that data and see what happens. On the Word document, problem number 1 below says interpret the point 1250. Well, what does that mean? Good. So that's how we would graph it. So we're on the X12 and up 50. And what does the 12 represent? Okay, and it's the trunk's diameter, right? So in inches, so a 12-inch diameter tree and then we'll have, what's the 50 representing? Yeah, 50 board feet. Right below that, it says interpret the point 36,970. A similar interpretation, we'd have 36-inch diameter, it's a whole yard. We'll have, yes, 970 board feet. Well, we're going to have to, unfortunately, flip back and forth between page 1 and page 2. On the next page, page 3, it says, estimate the number of board feet for a trunk with 20-inch diameter. If we look back at the first page, you're going to notice that I intentionally left a couple of the rows blank. And so if we were to look at 20 as the diameter, how many board feet do you think we could get out of it? And we can also look at our trend of our points and estimate. How much? 200. Do you think that that point would be up there at 200? Does that seem reasonable? So in our table, we can write 20 and then 200 right next to it. And over on page 2, we can also write that. Problem 4 says, describe the behavior of the graph. Describing the behavior of that graph is talking about trends that you see. So what trend do you see? Okay, it goes up. So as the diameter gets larger, what happens to the board feet? Okay, the board feet increases. Now, would this be a straight line graph? No, it's got a curve to it, right? So this is what we would consider a quadratic graph. I know it doesn't look like all of a quadratic, but if we connect the points that we do have, you can see that it's like the right-hand side of a parabola. And going back to page 2 then, describe the behavior of the graph. As the diameter increases, that's right. Yes, exactly. So number 5 is a quadratic trend. While you were plotting the data, I went ahead and loaded the data into Excel, and I created a scatter plot with the data. And then I asked it to create a trend line, which is a new feature in Excel, and it's really nice. So we can see our points are connected. Our trend line is that the equation would be y equals almost 1x squared minus about 10x plus 22. So that would be a quadratic that you're familiar with and seeing. And we're going to write that equation down. I'm going to first write it on the board so I can continue to maintain seeing it. I believe so. Yes, what equation matches this trend line? So I'm going to write y equals x squared, because it's just a 1, minus 10x plus 22. Number 7 says, using the equation, what is the estimated number of board feet for a trunk with a 20-inch diameter? We had guessed that a 20-inch diameter would have how much board feet? 200. So with this equation, what we're going to do is we're going to put the 20 in where the x is and carry out the arithmetic. I would grab a calculator and type this information in. Several of you did type those into your calculator, and what value did you get? Good, 222 board feet. Question 8 says, how close are your answers from question 3 and question 7? They are close. Now, originally we had said 200, right? So if we subtract the two values, 222 and our estimate of 200, we can see that we were off by 22. But we were close. Equations help us to create trends that we feel more confident in our values instead of providing just estimates. Problem 9 is very similar to problem 7. It says, using the equation, what is the number of board feet for a trunk with a 30-inch diameter? Sorry, thank you, 38. We're going to plug 38 into the equation this time. Y equals 38 squared minus 10 multiplied with 38 plus 22. Inch diameter, then the tree would have 1,086 board feet in it. It's a lot of board feet, but it's also a really wide tree. Hard to grow those in Montana. Our winters are just so long that the growing season is too short for them to get very big. That's why we're good at lodgepole pines. Number 10 says, is there a minimum point for the graph? And if so, what would it be? Remember with our parabolas that if we have a graph that's opening down, this top point, we talked about this being a maximum, and then if our graph opened up, our vertex was a minimum. If we look at our graph, do we have a minimum point? Yeah, we do have a minimum point. And why do you think it is 12? Right, the tree has to have you have to measure it at a certain height. And then if we cut off a tree that was smaller than 12 feet or 12 inches in diameter, we'd be cutting it off prematurely and probably losing a lot of profit. So that is a minimum. Is there a maximum point for our graph? In theory, no, right? In life, can we make a tree that grows infinitely? No. There is a point to which this tree is going to kill itself, right? Or just not grow to an infinite size, or also takes over the earth. So on 11, where it says, is there a maximum point for the graph? We could say no, and then we could say, but in real life, it'll never go to infinity.